This video is for the revision of why transition metals in some of its oxidation states are colored. Before this revision, you should already revise what's the definition of transition elements. You should already know what are the electronic configurations of transition elements and ions, and you should already know what's a complex ion. In SL, you learn that the s orbital looks like this. It's spherical in shape, and the p orbital is a dumbbell, this way or this way. And these are actually what the d orbital looks like. So you don't need this, but I do want to show you this. Let's also revise what's a ligand. A ligand is an anion or a neutral molecule, and this must have a lone pair of electrons at least. And this lone pair of electrons are going to form a dative bond. So for example, if I have Fe, H2O, 6 of it, so that's Fe2 plus. This Fe2 plus will have partially filled d orbitals, and this H2O, of course, it has lone pairs of electrons, and it's going to form a dative bond like that. So ligand must have a lone pair of electrons at least and can form a dative bond to the central. We'll cover 3 shapes of complex with 6 ligands, octahedral, with 4 ligands, there's 2, tetrahedral and square planar. In this video, we're not going to focus on the shapes of the complexes. We're going to focus on the color of the complexes. So not so much focus on this octahedral, tetrahedral, and square planar. In gaseous transition metal ions, all the 3d orbitals, they have the same energy. We call that degenerate. When they are surrounded by ligands, then they split to 2 groups like this. Okay, this splitting is caused by the repulsion between the electrons from the metal ions 3d orbital here with the electrons from the ligands. If you read the textbook, you'll see there's a clause that says 2 of the metal ion d orbital point directly at the ligands and so are raised in energy, whereas the other 3 d orbitals point between the ligands and are lowered in energy relative to the other 2 orbitals at the top. So like what I draw just now, there's 2 up here and there's 3 down here. Okay, what does that mean? I'll show you the picture up there. Let's recall what an octahedral shaped complex ion looks like. So in this picture here, so I have the lone pairs from the water, which is actually from the oxygen, points at the copper, and 2 are coming out from my page. 2 are going into my page, and 1 up and 1 down. So this is an octahedral shape. Okay, when you look at this octahedral shape, let's try to overlap it onto this picture. Okay, so there is X, Y, and Z here. So let's imagine that as the X, Y, and Z here. So overlap it from this picture to this picture. Okay, let's try that. You'll see that when the ligands approach, as in the water, so the lone pair from the water will approach the central via the axis here, the XYZ axis. So it'll approach from here, 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 here. So 1, 2, 3, 4, that's 4 ligands. 5, 6. So the ligands lone pair is going to repel the electrons that's inside these orbitals, this 1, 2, 3, 4, 5, 6. So the orbitals, these 2 orbitals, they point directly at the ligand. Okay, so this one points directly. Let's compare it with the other 3 orbitals. See, does it point directly at it? So just to remind you, all these 5 exist at the same time. These 5 are actually to represent these 5 d orbitals. Okay, now the other three. So we know that the ligands come in here, 2, 3, 4, 5, 6. Do you see that the orbitals here are in between the axis? So it doesn't point directly at the ligands. It's in between the ligands. It's in between where the ligands are approaching. So this, although there is some repulsion, the repulsion is less and lower in energy level compared to this two just now. This one definitely does a lot of repulsion because it points directly at the ligand. So this two that repels so much is represented by this two box that is higher in energy level. And these who are in between who won't really bump into the electrons from the ligands. These in between ones has a lower energy level. Okay, so if going back to your, let's go back to your textbook and read that sentence again. Two of the metal ion d orbitals point directly at the ligands and so are raised in energy level. So that's the two that we mentioned just now, the two box that is higher above. Whereas the other three or d orbitals point between the ligands and are lower in energy relative to the other two orbitals, the d orbitals. So they were talking about this two and this three. So if you know this picture, this two and this three. Okay, enough about imagining what they look like. Let's go back to our topic, which is why are they colored? So the first story was about why were they split? Okay, after the splitting, energy in the form of visible light, it will be absorbed when the electron from down here, so some of the electrons, they are partially filled, right? So that some of the electrons down here, they absorb the visible light that I mentioned just now. So then it gets promoted because that's energy. So the electron from the lower set of orbital will be promoted to the higher set of orbitals. Okay, when it's promoted like this, it will absorb some of the visible light. So in FL, we saw that E equals to HV, and this is proportional to 1 over lambda. This is the wavelength of the light. This energy gap is in the visible light region. So if it absorbs red color, you're going to see green color. If it absorbs yellow, you're going to see violet. So like copper sulfate, it absorbs orange. So you saw copper sulfate as blue color. So that we say that it's complementary. Complementary color. So we will observe complementary colors from what it absorbed. So they will only be colored if there's a ligand or there's ligands approaching it. So you saw just now when there is no ligands around, it will just be degenerate, which means all 5 are the same energy level. Then there's no promotion of anything. So the whole story won't be there about colors. Okay, so first of all, there must be ligands that approach the central ion or atom. And the second thing is there must be partially filled d orbital. Okay, because it needs to have space to promote. Then it can absorb that energy and you can see the complementary color. So for something like titanium 4+, let's look at the electronic configuration: 1s2, 2s2, 2p6, 3s2, 3p6, 3d2, 4s2. We take out 4 electrons. So from the outermost first, 1, 2, 3, 4. So there's no partially filled d orbital. That is why it has no color. So titanium 4+ has no colors because this whole splitting did not happen. Different metals would show a different color because they have a different gap of splitting here. For example, in IG, you already memorized that copper 2+, it's blue, and Fe2+, it's green. but it's actually not copper 2 plus that is blue. It's actually copper 2 plus with the ligands that is blue. So we actually draw it like this. And Fe2 plus with 6 water, that's green. As for metal ions have the same number of electrons, such as Mn2 plus and Fe3 plus, so they have the same number of electrons, then the one with a larger nuclear charge is going to pull the electrons closer towards itself, which means the repulsion is even more. So if the repulsion is more, the gap, the energy gap that we see is even bigger. So the one with a higher nuclear charge has a larger gap here. So greater splitting, greater energy difference here. Okay, next thing is the oxidation numbers. So we can have Fe in 2 plus or Fe in 3 plus. So similar explanation as the one we had just now. The one with the larger charge will pull the ligands closer towards itself, therefore a larger repulsion. There's more repulsion, so the gap is going to be larger compared to the one with lesser charge. How great is this splitting also depends on what ligand it is. This list is available in your data booklet to refer. So in exams, you can refer to the data booklet. The ones on this side causes a larger split, so larger energy gap here, and these causes a smaller energy gap difference here. Okay, so for example, ammonia would cause a larger splitting than water.